much. I would like to start by acknowledging the many co-authors that have made this study possible, and in particular, Jeff Servinghausen and Ed Brook, who have measured the gases that are at the key of the presentation for today. But I want to start by talking about the ocean overturning circulation. This is a nice, simple schematic that shows how this vast network of currents moves around huge amount of energy, heat, nutrients, and carbon. And it's driven, of course, by the formation of deep water, both in the North Atlantic with the North Atlantic deep water and around the Antarctic with the Antarctic bottom water. And that ocean current, as we know, is incredibly important. It has absorbed about 40% of the CO2, and about 1/3 of that in the Southern Ocean. It also absorbed 90 to 96% of the heat from the greenhouse gas emissions, and again, about 2/3 of that in the Southern Ocean. Antarctic bottom water accounts about for 40% of the ocean volume, so that's a very large dial if we play with it. And of that, 40% of that Antarctic bottom water is formed in the Ross Sea. But we also now observe changes, of course. Antarctic bottom water has freshened and contracted. We see from observations in the Weddell Sea that Antarctic bottom water has reduced by about 30% since 1992. And in the Australian sector, we see that Antarctic bottom water has been quite variable, but has shown more or less a net decrease. The way Antarctic bottom water, at its very simplified, and I hope I don't offend all the oceanographers in the room now, is formed, is really links it back to Antarctic sea ice formation. And so it's really critical that if sea ice changes and ice shelf configuration change, we expect Antarctic bottom water or deep waters to change as well. And of course, we see very, very significant changes in sea ice, which are dominated by changes in the Ross Sea. So we all have become quite used to the decline in Arctic sea ice. But until 2016, Antarctic sea ice has shown a slight increase. And then something really remarkable happened in 2016. We suddenly saw this really extensive drop in Antarctic sea ice conditions, which is dominated by a change from a growth of sea ice in the Ross Sea to a decrease of sea ice in the Ross Sea. And just to remind us about the magnitude of that, in the first 3 years after 2016, Antarctica lost the equivalent of 30 years of Arctic sea ice. This is really a fast, dramatic change. And 2022 was a previous minimum. But now when we look at 2023, and so this graph here shows the long-term average, and then 2022, the green line, you can already see that that was a very disturbing sort of deviation of our understanding of Antarctic sea ice. But then 2023 just looks really quite outstanding. It's not something that we would have, I think any of us would have predicted, any of the models could have shown. And again, if we think about the magnitude of that change, the last full month, August, we were missing about 2,500 million square kilometer of sea ice. That is larger than the Antarctic ice sheet. The Greenland ice sheet. This is a really, really large reduction in sea ice. So, of course, we should be also not just worried about the sea ice itself. That has many, many implications on the climate system. I'll just focus on the Antarctic bottom water connection and the rest of the talk. So if we want to know how this ocean circulation could change very rapidly, we can look at a past climate record. And this is the beautiful record of the Waste Divide ice core, led by a publication by Chris Buziard and the team, that looked at switches in this ocean circulation, the bipolar seesaw. And we have, in the glacial period, about 25 of those Dansgaard-Oeschger Ame-Band couplings. These Dansgaard-Oeschger events are very extreme. They rise local temperature in Greenland 10 to 15 degrees. The onset is within decades. It happens really, really fast. Duration can be 500 to 2,000 years, so quite a commitment. And in contrast, the coupling to Antarctica, the warming is more gradual. The warming itself is a little bit less, 1 to 2 degrees. But in this paper, the Waste Divide team really showed this beautiful coupling between, in the antiphase, between the two hemispheres. And that is linked to the overturning circulation, where in an interstadial we have a really strong North Atlantic cell of the overturning circulation, which gets Greenland and the North Atlantic warmer. And then in a stadial, we have the opposite. When Antarctic bottom water formation is stronger, we have a stronger southern cell, and with that, Antarctica is warming. And again, Weis divide showed this really quite remarkable relationship that was very relatively robust, where Antarctica would be warming, then suddenly Greenland would wake up and have a really strong warming, warm really strongly and abruptly. And then Antarctica would continue to warm for about 200 years before it starts to cool. And then the reverse would be true. Greenland would suddenly be starting cooling quite abruptly, and Antarctica again would continue to cool for about 200 years before it then starts to warm. So the classic bipolar seesaw. And this really fundamentally underlines how we anticipate and understand how energy is moved around with the ocean. So in comes the Rice Ice Core. The Rice Ice Core has been taken at this beautiful little Roosevelt Island Nuck, which is at the northern edge of the Ross Ice Shelf. Its principal focus of this project was really to understand how the Ross Ice Shelf in West Antarctica would respond to a warming world. It's a really good place to do that, because when you look at Roosevelt Island here in the cross-section, you can see that it's a rise that is where the ice is grounded 200 meters below sea level, and the Ross Ice Shelf is flowing around it. So the ice that accumulates on Roosevelt Island is locally accumulating, and it's coupled to the Ross Ice Shelf, but independent of it. So it can really monitor quite well what the Ross Ice Shelf is doing, while also being very sensitive to these ocean changes. So now we want to show you a couple of slides of data, and some of the really surprising information that we found from the Rice Ice Core. So here we can see the gas record in the top. So we're just going to zoom into the last of those bipolar seesaw switches, where we see the change in the ocean current during the Antarctic Cold Reversal. And the top two records are gas records, so there's no age difference. We are very confident about the relative dating of those and also the absolute dating of these records, and they link us through the methane to the northern hemisphere, while the delta 15N is a signal of snow accumulation or firn depth column, which I would sort of suggest is the Antarctic signal here. And then below you can see the West Antarctic Ice Core record, the Weis Divide Ice Core record, and the Roosevelt Island record. And now I want to focus you on just 3 data points on the thousands that we measured. Those 3 have become very important. So what we can see here is that the Antarctic signal changes into the Antarctic cold reversal before Greenland, and it does it by about 200 years. So rather than the thing that we have observed over and over again, and I feel a little bit like Christian Ohnheiser, sort of having the anxiety of actually showing something that goes entirely against what we thought to understand really well, that instead of lagging by 200 years, the Ross Seas seems to be leading by 200 years. And as I said, we're really confident in these ages. If we now look also at the temperature difference, and this is now both Antarctic records, the really well-dated Weis Ice Core and the Rice Core, which is very linked to the chronology of Weis Divide, we can see here also that Rice is leading by about 300 years. So when I now throw in a few more data than just the 3 data points, then instead of explaining each of those proxies, what they really mean, I'll just give you sort of the grand summary. We're looking at snow accumulation, dust, some proxies for sea salt or sea ice, a proxy for primary productivity, and then temperature. And what we see is that the very first thing is actually not the gases that change, but we see a change in the dust. That is followed by a change in the sea salt proxy, which also is linked to changes in the primary productivity and also changes in the gases. And then we see that change in temperature, where the Ross Sea is starting to cool faster than West Antarctica. So what does that mean? What we think that means is that we see first a change in the position of the southern westerlies. This is followed most likely by a change in the CS conditions in the Ross Sea. And this is followed by changes that is expressed in snow accumulation, so really moisture source, atmospheric circulation pattern. And ultimately, that led to an early onset of the Antarctic Cold Reversal. So that would really suggest that potentially the Ross Sea could see the change that is yet to occur in Greenland 200 years later, before the actual event occurs. And that really suggests that we might need to start thinking whether there's a regional response that could be much faster than an Antarctic-wide response to this very strong, globally important mechanism. Thank you.
Thank you very much, Nancy. Are there any questions?
Thanks for a very interesting talk. I'm wondering if you have checked the deuterium excess in the ice core.
Yeah, thank you. We have a lot more data, and the deuterium excess does some very strange things. We don't understand it yet, but it's quite variable over this time period. We'll be happy to talk to you more about it.
Got time for a quick question if there is one? Okay, thank you.
Thank you.
So we're next moving on to our invite